I'd like to welcome Dr. Zetian Mi to our monthly UMRA seminar. An alumnus of the University of Michigan, Dr. Mi received his PhD in applied physiology in 2006. He returned as a faculty member in 2016. Most recently, he was an associate professor of electrical and computer engineering at McGill University in Canada, where he received several major awards, including the Engineering Innovation Award. He is currently a professor with the U of M College of Engineering, Department of Electrical Engineering and Computer Science. His teaching and research interests are in the areas of low-dimensional semiconductors and their applications in photonic, electronic, clean energy, and quantum devices and systems. He received the Science and Engineering Award from the W.M. Keck Foundation in 2020 and the David E. Little Research Excellence Award in 2021. He currently serves as the editor-in-chief of Progress in Quantum Electronics. His very impressive bio includes over 100 publications and hundreds of citations. So please welcome Dr. Mi to our meeting.
Thank you for the kind introduction, Wai. It's my great honor and pleasure to be here, and this is really a very impressive group. Very nice to be part of this in this afternoon. I will talk briefly some of the work we have been doing in my group and also in the broad field of clean energy. So in my free time as a professor, I also co-founded two companies, NS Nanotech and X Fields. Both are headquartered in Ann Arbor, so they are commercializing some of the technologies I'm going to present here today. And feel free to stop me if you have any questions anytime. So let's take a look at the challenges we are facing in this century. A lot of them are related to energy and also environment sustainability. So the biggest challenge from my point of view is related to the energy consumption, right? By end of this century, the primary energy consumption, even in the most conservative estimation, will reach more than 50 terawatts. And with the sharp increase of energy demand, it comes with many issues. The resources are limited. The steep increase in price, we have seen that, and even so in other countries like in Europe and other regions. And we also seen over the last couple of years huge issues with geopolitical instability, right? That's really ongoing around the world. And there is a clear need for renewable, clean energy resources on demand. And now let's take a look at the United States. So see what we are doing here, and are we making our contribution, doing our fair share? As of today, 80% of U.S. energy depends on fossil fuels on average, a little bit better in some states than others. And coal is responsible for 40% of U.S. power generation on average. And we do not see this will change in any dramatic ways in the near future. And last year, 2023, just over a week ago, is the hottest year on record. And so accompanied with that is global warming and huge environmental issues we face, not only in North America, but also around the globe. So whether we realize or not, many people, many scientists believe we are at the tipping point. By saying the tipping point is a 400 ppm CO2 concentration in atmosphere. So you can see this is increasing, and for a long time, it is believed that once we pass the 400 ppm, the damage, the consequence of CO2 concentration in atmosphere will be irreversible. But what makes this even more problematic is this trend continues and continues dramatically. So there are always room for innovation, and from history we always see that when there is a challenge, scientists, engineers come up with very innovative solutions. So we turn this problem into nature, see what happened over not the last millions of years, but through billions of years. The reality is every oxygen molecule we breathe in this room comes from natural photosynthesis. And it's a process that converts carbon dioxide and water into oxygen and clean chemicals, fuels. And in this process, it utilizes only solar power, solar energy. So the natural photosynthesis works very well because of the long time. We are talking about geological time, right? Millions of years. But the reality is the efficiency is very low, 0.6% on average. So the question is, can we be inspired by nature but do much better job than what nature does, improve the efficiency 10 times, 100 times, and be able to generate clean chemicals, fuels directly from solar, from carbon dioxide, from nitrogen, from water. And if we delve deeper into the natural photosynthesis, essentially it's a very complex reaction, chemical reaction, but at very high level it has two steps. The first step is break down the water molecules, give us oxygen and protons. And second step, it break down the CO bonds and combine with hydrogen, we get carbohydrates, the sugars, fossil fuels, and those things we need, we rely on today and in the future. So if we can do that, if we can generate clean chemicals and fuels through solar-powered artificial photosynthesis, then not only we can address some of the most important energy issues, the environmental sustainability, we can also generate clean energy on demand whenever, wherever we need that. And one immediate application will be related to the fuel cell vehicles. So fuel cell vehicles will be far better than some of the IC vehicle or even electrical vehicle, which I will discuss later. Is really the next generation technology moving forward. So, and let's talk about the first step. The first step for artificial photosynthesis is to break down the water molecules into oxygen and hydrogen. And the first question, why hydrogen, right? We have electric vehicles which are really produced at reasonable cost everywhere almost. Why do we still need hydrogen, especially for the transportation? And there are many reasons. I just want to mention one. So for lithium-ion battery, it has some fundamental challenges and issues. For example, the very limited range, very heavy weight. If we put lithium-ion batteries into a heavy-duty truck, and then you quickly realize the majority of the weight the truck has to carry will be the battery itself rather than the goods. So it's a huge issue, right? 10 to 20 tons, long charging time, and hydrogen fuel is the highest energy density and have much greater range, 10 times less weight, and the charging time is similar to gasoline in just a few minutes. So hydrogen demand is projected to increase by tenfold over the next 3 decades. As you can see, it's a huge market. It's driven partly by automotive industry, but also needed by many other business sectors. And but the reality is, as of today, over 95% of hydrogen is produced using a method called steam methane reforming. Hydrogen itself is clean. You burn hydrogen, you only get moisture or water vapor and warm air that you produce, a very clean process. But the reality is over 95% of hydrogen we produce today is from a very non-clean process, steam methane reforming. For every kilogram hydrogen we produce, we emit more than 10 kilograms of carbon dioxide, and this is generated in centralized facilities, so transportation of hydrogen is a huge issue, and this process also gives hydrogen that's not clean enough for fuel cell vehicles. You still have to do downstream purification. So generating hydrogen today costs about $2 to $3 per kilogram, but if you buy it on the market, it will be $20 to $30 dollar per kilogram because of those fundamental issues, not to mention the huge CO2 emission in the process. So in order to make this a more practical green technology, we must go beyond the conventional, this gray hydrogen. That's the first generation hydrogen 1.0. Second generation hydrogen 2.0 is to collect the CO2 emitted in the generation process and store it underground or somewhere, so-called blue hydrogen. It does not fundamentally address the CO2 issue, but at least temporarily it does not release in air, so blue hydrogen. But the ultimate solution is the green hydrogen, following what nature does. Is solar water splitting. You generate clean green hydrogen utilizing the abundant solar energy. But getting there is not trivial. So it has drawn lots of attention. For example, Bill Gates really think the hydrogen is be able to generate a cheap green hydrogen is a huge deal in helping the energy transition for carbon neutrality, for environmental sustainability. And we also seen in the news over the years, so transition to clean energy carbon neutrality is no longer just from the environment point of view, in many places required by law. And there's already carbon tax in many countries, and very soon it will be in US and also many other countries, which will provide the incentive and the motivation for faster transition to clean energy. So now let's come back to the basics. What does it take to break down water molecules into hydrogen and oxygen? So basically, the very fundamental process is shown here. You have a light absorber, and it absorbs solar energy, generates charge carriers, electrons and holes in the semiconductor. And those charge carriers flow to the surface, react with water molecules, so essentially break down the HO bond to give us protons, which give you hydrogen, and also the oxygen released in air. So from a conceptual point of view, it's relatively a simple process. It requires efficient light absorption, charge carrier extraction, then reaction with water molecules, and produce hydrogen oxygen. The minimum energy required for this process in theory is only 1.23 volts, right, which is very low voltage. But in reality, it's very difficult because you need to be able to maintain the efficiency, have long-term stability, and be able to do that not only for hours, but days, months, and years without any performance degradation, and also be able to have the material that give you low cost and scalability, scalable manufacturing. So traditionally, this has been done in a chemistry field by chemists, chemical engineering, and now it's drawing attention really from electrical engineering, from physics community collectively to address some of the very fundamental issues, not only on the chemical reaction, but on the materials, on the integration, on the engineering, and the system level. So this effect, the solar water splitting, this effect was actually observed a long time ago, 1839. And but then later on is the more prominent effect, a demonstration of photoelectrochemical water splitting was about 50 years ago, 1972, by Honda and Fukushima, and demonstrating using titanium dioxide with sunlight absorption, you can produce hydrogen and oxygen. So for those who may not be familiar with titanium dioxide, this is also the material you use in the sunblock. So you actually have, those are made of TiO2 powders. When you shine light, they block the light, mostly the UV light, and some of the reaction probably happening on your skin, whether you realize it or not, right, at a very low efficiency level. Okay. So if this technology can be made more efficient, scalable, then really provide a very appealing approach to address the fundamental issues, the challenges we are talking about. For example, it's entirely based on solar energy, environment safe, friendly, and you do not produce other byproducts, and suitable for large or small scale, as we have seen here, is relatively simple process. Okay, so then you can scale this up as we do with the solar cells, right? Instead of producing electricity, you're producing hydrogen. You can produce directly on site. You can replace the natural gas by hydrogen. In many places of the world, the natural gas is already blended with hydrogen. So here you can blend with clean hydrogen. So you can see there are many uses of that, not to mention the fuel cell vehicles, among others. Okay, but you can see for a long time, although the chemistry, physics are relatively well understood, was not becoming a real technology, and for several fundamental reasons, because the material we use, for example, TiO2, titanium dioxide, can only absorb a very small portion of the UV spectrum, and therefore the efficiency is very limited. So about over 10 years ago, we started working on this topic. And that time we look into a very different material called gallium nitride. And for those of you who are not familiar with gallium nitride is a material being used in LED lighting. So LED light bulb is based on gallium nitride. It is based on the invention by 3 Nobel laureates, 2014. They got the Nobel Prize for their invention of the very efficient blue LEDs using gallium nitride. Today, gallium nitride is one of the most produced semiconductors for LED lighting, for high power and high frequency electronic devices. For example, even some of the components in your smartphone, and there is a chance that this technology, this material is already there. And those are already a huge market. For example, LED lighting is over $100 billion, power electronics also tens of billions of dollars, and growing very, very rapidly. So you can see that this material is scalable, manufacturable. If we can turn this material to be a very efficient catalyst to drive water splitting hydrogen fuel production, you can see the scalability manufacturing issue, fundamentally speaking, is not a bottleneck. And we have found another very important property for this material is that their conduction valence band edge positions can be tuned. So in order to have very efficient solar water splitting or other artificial photosynthesis, it is very important to have narrower band gap so that it can absorb very efficient sunlight. But that's not the only requirement. You need to make sure that when the material absorbs sunlight, it generates charge carriers with the appropriate energy to react with chemical species, for example, water molecules, and be able to break down the water molecules. In order to do that, the conduction and valence band edge must straddle the redox chemical potentials. And with the nitrides, you can alloy with indium, antimony, other elements. You can narrow down the band gap. You can tune the band edge potentials. So give you tremendous flexibility in designing, tuning the material properties to meet the requirement for high efficiency artificial photosynthesis. So this is a very important discovery we made when I was still at McGill University in Montreal, Canada, about 10 years ago. And so based on that, we grew the materials. If you take a conventional gallium nitride material used for transistors, the power electronics, or for LED light bulb, it does not work. People tried and failed. The reason is, I'll explain later, the surface is very important. You need to get into the right structure, utilize the right facet surface of the material, be able to exploit all the very unique photocatalytic chemical properties for the very efficient reaction. So we, instead of looking at the conventional planar structure, we developed these nanostructures, and the very first generation we developed, and then later on we have a much more controllable process. And the size of those structures is about 1,000 times smaller than the width of a human hair. And you can control the size, position, spacing, morphology, properties, which is really a game changer, allow us to really break the efficiency bottleneck of this material for photosynthesis. Okay, so when we dreamed to build artificial photosynthesis device, we were really overwhelmed because nature has accomplished this through millions, billions years of evolution. And if you just take a leaf and take a look at the reaction, it's remarkably complex, right? So in our first step, we say, hey, look, we will only look into the water splitting. We want to build a wafer, the semiconductor wafer, like a solar cell. Can we achieve very efficient water splitting, generate oxygen and hydrogen? If we can do that, we already accomplished a very important step for clean energy generation. And this will also serve as a basis for future artificial photosynthesis technology, which I will discuss later. So here just show the schematic of we have the wafer. Now we grow about 3 inches in our lab. In industry, you can go to much larger size. We have this micrometer thick height nanostructures, or forests of nanostructures. We put them on top. We also incorporate with suitable metal particles, which just a few atoms in size, and we integrate them together. So we started this almost 12 years ago. Started with a summer undergraduate student. It worked. It show bubbles, and you see hydrogen oxygen generation when you put the material in solution in water. You shine sunlight, but you can see the efficiency is really low, less than 0.1%, extremely low. And through the years, we really understand some of the very fundamental limitations and be able to design devices with far better performance. I will not go through the details, but instead just give you a high-level overview. So we first learned how to integrate the co-catalyst better and be able to engineer the built-in polarization field in the material, so allow more efficient charge carrier extraction, and also integrate with silicon, so we have better performance, better voltage, and more efficient reaction. And more recently, we look into the entire reaction and system design through the thermal reaction engineering. We have further dramatically improved the performance. So there are lots of details. I will not go through that. Instead, I want to show you some very interesting phenomena we have observed in this process that really allow us to dramatically improve the performance. And some of this actually quite entertaining. Okay, I just want to give you 2 examples. And the first one, so the material we use is gallium nitride, has a Wurtzite structure. So for those of you who are familiar with crystals, semiconductors, they have very different faces and planes. So the conventional gallium nitride used for LED lighting, for transistors, are always on the top C plane. So 99.9% of the nitride research really deal with the top C plane. And so we ask a very fundamental question. So you have the C plane, semipolar plane, nonpolar plane. So they have very different properties, different polarization field, and different Fermi level pinning, etc. For artificial photosynthesis, which facet is better? And so which is more active? And more importantly, when you put a semiconductor in solution, which often strongly acidic or basic solution, even in water, like seawater, is actually quite corrosive. And then you shine light, often concentrated sunlight. You operate this at a high temperature. Those are extreme conditions. What happened to the atoms on the surface? Do they get corroded? Do they get etched? Etc. So, and once we develop this nanostructure, we have done some very simple experiments. If we only expose the top of the C plane, so which is the blue curve here, you can see there's no current, no performance, and that's why the efficiency is so low using conventional nitride materials. But the moment we expose the nonpolar, which is the side wall, and you can see a dramatically improved performance, higher current density, higher voltage for the same material, same condition. So the surface facet matters. Not all the surfaces are equal. And the reason that this material was the extraordinary photocatalytic effect was not discovered before, because people are really relying on the top C plane. And actually, the one that really works is on the side wall. And then on the side wall, also very interesting happens. So traditional belief is that you take the semiconductor surface, you put into a oxidative reaction condition like water splitting, the surface gets oxidized or corroded. But on the nonpolar surface, remarkable things happen. So instead of getting oxidized or corroded, the gallium nitride gets a partial oxidation. So some of the nitrogen atoms are replaced by oxygen. So the surface, the very outer surface, 1 nanometer, is transformed to be a new surface called gallium oxynitride. And after about 1 nanometer, this partial oxidation stops. This gallium oxynitride is photocatalytically active, is extremely stable in harsh conditions. So it protects the surface and make the material much more robust, much more efficient. And you only see this phenomena, this effect, when the nonpolar side wall is exposed. If you expose the conventional C-plane, it just gets oxidized or corroded, and the surface, the activity get degraded over time. And so with that, you can see over time, the performance gets better. You get higher current density, higher voltage, which translates into better performance. And this was actually jointly discovered with research scientists in Lawrence Berkeley National Lab and Lawrence Livermore National Lab. And they have been working in this field for decades. And when they test our device, they see this is the first time a device that performs better instead of degradation. And so this really gets a very important step to break the performance bottleneck, especially the stability of this artificial photosynthesis. And 3,000 hours continuous operation. It took the students almost 6 months to complete this. And if we have to stop this because of the student graduation, but otherwise lasts forever. So it's if you translate this into 5 hours illumination per day, like typical conditions in Michigan, this is 1.5 years continuous operation, no degradation. Yeah. And another very entertaining aspect is for chemical reactions, you have forward reaction, but there's always a backward reaction. So how do you promote the forward reaction, suppress the backward reaction? So again, let's take a water splitting as an example. What we like to see is you have the forward reaction, you generate hydrogen and oxygen, but you suppress the backward reaction, the proton, oxygen, the recombination, right? But the reality is any catalytic effect, any chemical reaction, both are happening at the same time. Okay, so for a long time, no one really paid much attention to this. But once we start improving the performance, we quickly realized this is a fundamental limitation. And so what we did is, this accidental discovery by one of my students is when we perform the reaction at, say, room temperature, 30 degrees, 40 degrees Celsius, it gets a few percent efficiency. But if we increase the reaction temperature, even to 70, 80 degrees, you can see a dramatic improvement in efficiency for otherwise identical conditions. And then we have done more theoretical study, and I will not go into details. What happened is when you go to higher reaction temperature, you very quickly suppress backward reaction. So the backward reaction is release energy. So higher temperature, you suppress that, you make the forward reaction much more efficient. So among several things we did, we can quickly improve the efficiency, okay? So what's really interesting is semiconductors, they like to operate at low temperature. For example, solar cells, they perform better when the temperature is cold. As long as there is enough sunlight, the temperature colder, then the performance better. But for chemical reaction, they want to operate at high temperature. So the question is, you are combining the two, and what will be the optimum conditions? So the overall efficiency matters. Really, to get this happy marriage, we identify the optimum temperature for this specific reaction is around 70 degrees Celsius. And this 70 degrees Celsius, you can achieve that by using concentrated sunlight. I'll show you later. And you just insulate the reaction chamber. Even in winter in Michigan, we can heat up to 70 to 80 degrees Celsius, dramatically improve the efficiency. And you can do that even just in 20, 30 minutes. So And so this is really something we think is really a big step forward in this field. We do utilize the previously wasted infralight of the solar spectrum to heat up the reaction chamber, to speed up the reaction, dramatically improve the efficiency. Now we reach over 9% utilizing only solar energy. We have gone further just using, for example, tap water or seawater gets similar performance. And this really paved the way for future practical application, manufacturability, and reduce cost at the system level. So I want to show you a video. Let me make sure it works. So this is a video we took in November, and it's really a relatively large-scale demonstration. For those of you who are familiar with North Campus, it's on the roof of the Wilson building. So it's a 1 meter square Fresnel lens. We concentrate sunlight into the reaction chamber, just about a few inches. Inside of the reaction chamber, we have our photocatalyst wafer immersed in water. You can see huge amount of hydrogen bubbles are produced in real time. In this process, there's no wire, no electricity. The only energy input is solar energy. As I mentioned, it's November time. And you can see the chamber temperature already about 75 degrees Celsius. And we have also scaled this up. And this is the setup we started during the pandemic. And that's near the solar farm on North Campus. And we construct this, and now this can go up to 1 kilowatt. Really scale this up. And this is arguably probably the only concentrated sunlight artificial photosynthesis in the university in US, to my knowledge. So we really have gone a long way from lab all the way to demonstration. And now currently we are working with NX Fields, as I mentioned earlier. It's a spin-off from University of Michigan to commercialize this technology. And the material we use, gallium nitride silicon, those are the two most produced semiconductors. And we envision that you follow the scale up of solar cells. So instead of producing electricity, we produce clean hydrogen. And so electricity, you still need to have a battery, everything not storable, but hydrogen storable. Especially clean hydrogen can be directly produced on site, can be directly connected to a fuel cell vehicle, or blended into natural gas. So how to produce 50 kilogram hydrogen per day? Is that feasible? What does it take? Okay, so this depends on a few factors. For example, the efficiency. If we operate at 1% efficiency level and 1 sun, then the area of the wafer we require will be 27,000 square meters. It's huge, right? You can see the cost will be high. By utilizing our approach at high efficiency, say 10%, we concentrate, let's say 500 suns. The area wafer we use is only about 5 meters square. So it's really about 2 by 3 meter, right? So the size of 1 or 2 tables. And you can produce 50 kilogram hydrogen per day in the typical good weather here in Michigan. And the 50 kilogram hydrogen, what does that give to you, right? So if you get a typical fuel cell vehicle, 50 kilogram hydrogen can allow you to drive over 6,000 miles. Yeah, it has a very high energy density. So that's only the first part of the photosynthesis. There's a lot more. And so with this, the development of the efficient catalyst for solar water splitting really sets the stage for many, many remarkable things in the future to, for example, reduce carbon dioxide to clean chemicals and fuels, turn natural gas to liquid fuels, and convert nitrogen to ammonia, the fertilizers. And so all those things, there are still lots of fundamental challenges. For example, those very complex chemical reactions currently have very low efficiency and also has stability issue, have product selectivity issue. So those are fundamental science engineering challenges. But as we see that over history, that we always can be inspired by nature, we can do far better than nature. And there I strongly believe that we can bring this photosynthesis technology to be far more efficient than what nature has done over millions or billions of years. Just a few examples. Some are directly connected to us here in Michigan, because when we talk about energy environment, we always think, okay, this happening into North Pole, Antarctic, or Africa is not here in Michigan, but it happens here. It affects us. It affects our life. It affects our health. It affects our grandchildren. Okay, just take one example. So during summertime, and if you look at the lake area, you see that the color often blue, green. The reason because algae, you have huge amount of algae growing in the lakes. And why do they grow? Because there's huge contamination. There's nitrate in the water, right? Even in the water we drink every day, there is nitrate. That causes huge health issues, right? 60 million people in the US. I don't know how reliable this number is. It's over or underestimated, but a huge number are contaminated with elevated levels of nitrate, which causes cancer, other disease, right? Huron River, we have heard a lot of the issues about Huron River over the years, right? Our water comes from there. Okay, so the nitrate, if we can, through artificial photosynthesis, can utilize solar energy to convert nitrate into ammonia, it is a very complex reaction. But if we can do that, we can turn to waste into fertilizers, right? Then address some of the environmental issues and at the same time can provide some very useful stuff we would need. Okay, so just one example, we extend the technology we have developed for solar water splitting and integrate with suitable co-catalysts. It's a very sophisticated device engineering chemical reaction process. I will not bore you with the details, but just want to show you that we can reduce nitrate to ammonia with very high selectivity. And the efficiency is still low, but there's already a path moving forward to do something useful with the technology we have developed. And also let's talk about the urea synthesis. So urea is each year nearly 200 million tons of urea is produced because it's needed for farming, etc. And the market size is over $100 billion. Whether you believe it or not, the urea synthesis in this process, every year we emit over 1 gigaton of CO2. And that's more than the CO2 emission from the aviation industry. And the reason is because the urea synthesis is a very complex process. You first need to convert CH4, the methane, essentially natural gas, to hydrogen, and then your hydrogen and nitrogen combined together give you ammonia, and then ammonia and CO2 combined give you urea. A three-step process based on the invention by Haber and Bosch over a century ago. Those two got the Nobel Prize. So it's a 100th century old technology, very energy intensive, huge CO2 emission in this process. Okay, so can we be inspired by nature and be able to do this? We utilize solar energy. So this is some of the process we are building to utilize solar-driven process, combine nitrate and CO2 in air to produce urea. And studies have shown this is indeed feasible, and we are working on the efficiency and stability. And as we did in solar water splitting, it's just a matter of time to really overcome some of the performance bottleneck, make it more attractive. And there are other fundamental issues we also need to address. For example, natural gas. In the US, there are 500 trillion cubic feet of proven natural gas resources, right? We export natural gas to Europe, to many other places. But the other side of the story you probably do not hear, because many people, they will not tell you, is that 4 trillion cubic feet of natural gas is vented, burned as flare gas per year, right? Okay, that costs about $20 billion, but that's not the most important issue. The most important issue, every methane molecule we release in air is 20 times worse than CO2 in terms of greenhouse effect. And look at the numbers, 4 trillion cubic feet each year. And those are the numbers people can track, and what happens for things people don't know. So if we can convert the natural gas methane into liquid fuels, methanol, right? It's storable, transportable, it's clean chemical, it's a feedstock for many things we need. And this will address a large part of the issue. And just want to show you that this is indeed also feasible, but you need to have a different co-catalyst integrate with gallium nitride and also very, very complex chemical surface reaction engineering involved. Indeed, it's possible to convert natural gas directly to methanol with reasonable selectivity and efficiency. So I took this from a review article published a while ago, is that in the future, it is believed that our energy will be mostly from solar and solar fuels, and then provide not only clean hydrogen, but also carbohydrates for our society. So here we talk a lot about energy and the environment. And so many people may argue, if we run out of fossil fuels or we stop using fossil fuels, we can use wind energy, we can use nuclear power, etc. That's true, but there is a very fundamental issue many people didn't realize, is where do we get our materials, right? The clothes we wear, the medical pills we take, a large part of that the chemicals are from fossil fuels, right? But instead here, with artificial photosynthesis, not only we address the energy environmental issues, we provide new way to synthesize the chemicals, fuels we need in the future. So that brings to the end of my talk. I like to acknowledge all the wonderful collaborations I had when I was in Canada and here in Michigan, and also with many other places, universities, national labs, and companies throughout the years, and also my group member McGill and more recently at the University of Michigan for their dedication, and also all the funding agency and also support from University of Michigan since I came here. So with that, thank you very much. Be very happy to answer any questions.
Since you talk a lot about the gallium nitride, how abundant is it and where is it found?
Yes, great question. So as of today, there are not too many, in terms of earth abundance, right? But there could be other factors that people may need to worry about. But in terms of earth abundance, should not be a limiting factor.
How involved is your research with artificial intelligence, new modes of finding new ways of doing things?
Yeah. Thank you for the great question. And as you can see that the path to design the catalyst, identify the efficient material architecture reaction, extremely involving, time consuming, and there are lots of programming now is ongoing or getting attention to utilize machine learning, AI, to accelerate this discovery process.
Was the object of the exercise to produce hydrogen as a fuel, or was there some other objective?
Sorry, I didn't get the first part of your question. I wonder if you could repeat.
Was the object of the research to produce hydrogen as a fuel?
Yeah.
And if so, well, I just didn't understand quite what the objective was. It was to produce hydrogen as a fuel.
Yes, a large part of our goal is to produce clean hydrogen as a fuel through solar water splitting. And that's a short-term goal. The long-term goal is to build upon that to develop efficient artificial photosynthesis to reduce carbon dioxide into clean chemicals and fuels. I hope that answers your question.
I think, no, I don't see any other questions, so thank you.
one
One
more.
in the back?
Yep.
Oh,
As we know, we don't live on an island, and there's lots of places to find research partners. What other places are we looking for research partners to help propel all of this research forward?
Great question. Indeed, the collaboration, partnership, very important, and I'm very proud to say that University of Michigan really help a lot to develop a partnership not only with other institutions, but also with industry. So as I mentioned, since I came here, we co-founded 2 companies spin off from University of Michigan, and it's Nanotech and it's Fuse, and they are commercializing the technology we have developed here at the University of Michigan. And through this process, we also collaborate with some larger companies and on different fronts to help accelerate the technology transition. One more question there. Yeah.
hi. I think early on, one of the slides mentioned that companies are being asked to reduce their carbon emissions. And I feel like there was a headline that talked about one of the big oil companies.
Yep.
What is the response from big oil to your research and your findings?
Yes, so we actually, over the years, we also have had the opportunity to work with some of those companies. They are very open. I can take one example in Canada, in the province of Alberta. So the oil gas companies, they pay the government this so-called carbon tax. Essentially, for every metric ton of CO2 emission, they pay the government certain number of dollars, I believe $50 or something like that. Government collect this money and put into some program that really support innovative research like what we are doing here to develop new solutions to reduce CO2 emission. So it's actually becoming a win-win situation.
In Oak Ridge, Tennessee, they produced a saltwater reactor using thorium as the fuel. Surely this is very abundant, very easily available, and could produce a very large amount of electricity, which you could use for desalination, you could use it for producing oxygen, producing hydrogen. How come we haven't seen any advances in the liquid fluoride thorium reactors?
That's a great question. It's outside of my expertise on that. I do know some of my colleagues are working on that. I will try to find some more information for you on that.
Thank you very much. This was very interesting.
Thank you very much.
And informative. And also to be, again, proud of the University of Michigan for taking a lot of the leadership in putting this together as a consortium almost. So thank you very much.
Great. Thank you, everyone.